draw your eye to interesting things on the screen. So I was asked to address this topic, and I think it's of interest to a lot of folks who are looking forward to the utilization of water resources on Mars to support some kind of mission, whether it's robotic or more likely human, for various purposes. Obviously, water is useful for supporting human life and for supporting other kinds of life, and also has been identified as a key resource actually for manufacturing fuel on Mars. So you guys actually are the experts in those kinds of topics. I'm a planetary scientist, and my specialty is geological remote sensing, so I'm looking at things from the standpoint of geology, not as much from the standpoint of human exploration. But what I'd like to talk about is these very interesting regions that we've been able to identify on Mars that seem to contain H2O in the form of ice, in parts of Mars that are actually, relatively speaking, benign environments for surface missions. That is, they're not at the poles, they're not in places where you have many months of polar winter, and where the temperatures are not nearly so extreme as you might find in the polar and Arctic regions, where the ice resources are perhaps a little more obvious. So I think it's not news to anyone that we have all kinds of evidence that water has existed at the surface of Mars in the geologic past, and that water has flowed across the surface of Mars in many regions. What you see up here on the screen is an example from the boundary region between the highlands and the northern plains of Mars, where what we call the massive outflow events occurred that carved great canyons and moved a lot of material around. And over the years, folks who have studied these things have done calculations about just how much water actually was needed to do the amount of work, the erosion and the movement of material, just so that we can sort of get a handle on, well, what was the inventory of water on Mars in the past, and what might it be today. So this question of, well, just how much water does Mars have? Did it have? Might it have in the future? We like to express it in sort of a convenient shorthand unit, which is the global equivalent water layer. So imagine you took some huge amount of water and you spread it out evenly over the entire sphere of Mars. How deep would that layer of water be? So using the models of erosion and our understanding of erosional processes on the Earth, the folks who looked at those great erosional channels and outflow deposits estimated on the order of hundreds of meters of what we call this global equivalent water layer. It's not to say that Mars was covered by an ocean everywhere that deep, but that amount of water was needed to do that geologic work. So that's actually a significant amount of water, hundreds of meters. Now, it's not 100, it's not 1,000, it's on the order, because these kinds of things are very difficult to estimate, but it gives you an idea of sort of the ballpark, the order of magnitude of the amount of water that actually has been at the surface of Mars doing this work. Now, it could be that water was recycled and maybe some of the same water did the work twice, and that's why there's another reason why there's uncertainties on these numbers. But still, the water that we currently observe on Mars is much less than that. And I'll go through some of the numbers in a minute. But the question then becomes, where did all that water go? And this, along with the question of could Mars have ever hosted life in the past or currently, these are sort of the biggest questions about Mars that the planetary science community faces. Where did all that water go? We have a lot of evidence that there was loss through the atmosphere, that the water became vapor and somehow migrated to the top of the atmosphere and was stripped away by solar wind or other processes. The MAVEN mission that's currently at Mars right now is designed to address this very question, the atmospheric loss to space. In that case, Mars never gets the water back. It's gone for good, right? But there is very clearly still a substantial amount of that total inventory still either on or inside or both the planet surface and subsurface today. So we have no doubt there's plenty of H2O on Mars. It's just a question of exactly where do we go to get it, and where can we go where it's easy, relatively easy to access. So here's a short list, and it may not be complete, but it's a pretty good list, I think, of the current reservoirs of H2O on Mars as we understand them. Of course, there's the polar ice caps, and these are by far the largest confirmed known reservoirs of H2O on Mars. There's, and I'll get into this, there's ground ice that we've been able to detect from orbit and actually go and touch on the surface with a lander such as the Phoenix lander at the high latitudes. Now when I say high latitudes, I'm really talking about maybe what you'd think of as from the Arctic Circle to the pole on the Earth, so from 60 degrees latitude to the poles, north and south. And then there is a more recent evidence, and this is actually something I'm going to talk about in some detail, for ground ice in the mid-latitudes. Okay, maybe not right at the equator, but say in the 30 to 55 to 60, in that kind of middle temperate zone, like the zone that we're in, for example, here in Pasadena. There are what we believe are remnants of ancient glaciers and ice sheets from previous regimes of the Mars climate, and I'll talk about that in some detail. Water can also be tied up in minerals, hydrous minerals, such as gypsum is one example. We know that exists on the Mars surface. Groundwater, actual liquid water, at some depth below the surface, the temperatures are warm enough that that freezing boundary is crossed, and it's quite possible that there's liquid water in the subsurface of Mars. And then, of course, there's the atmosphere, which we know is extremely thin, and the water makes only a small fraction of the atmosphere, but it plays an important role because it is through the atmosphere that water can move around the planet. Okay, so this is a map. I don't know how it shows up on the screen. It does. Oh, looks pretty good. Okay. This mission that you heard in the introduction that I worked on, the 2001 Mars Odyssey mission, one of the first and important discoveries made by the instruments on that spacecraft, is represented here in this map. And this is using the Neutron Spectrometer. It's from the emission of neutrons that are reaction products of cosmic rays striking the surface of Mars. It's very sensitive to the presence of hydrogen in the soil, and we were able to map the entire planet of Mars and basically estimate the hydrogen, and here it's expressed, let's suppose all of that hydrogen in the upper several feet or about half of a meter of the soil. Let's suppose all that hydrogen was contained in H2O molecules. What would the fraction by mass of that soil be in terms of ice? So basically what we were able to confirm was what was predicted by a lot of folks who thought about these things, that in the highest latitudes, you can see here from 60 degrees to the pole in both the north and the south, there are these deep blue colors and even this purple color, which tells you that again, we're only sensitive with these neutrons to the upper half meter or so, but that soil is on the order of 20, 30, 40, even more percent ice right there at the surface, right there. So if you're willing to go to those very cold, nasty places that have, months-long polar nights, then go there and you'll find your H2O right there in the soil in that That's what the Phoenix lander actually detected in situ. Now, since those are rather challenging places for missions, for landed missions, the question is, what about these other areas in these lower latitudes, in the temperate latitudes, that seem to have at least maybe a few percent, maybe up to 10% equivalent water. Basically, the thinking right now is most of that is wrapped up in minerals, and that's not ice grains in the soil. And there are thermodynamic reasons that basically the atmosphere would tend to suck the ice out of the soil if there's a contact between the very dry Mars atmosphere and the ice grains. And so based on those arguments and also what we've learned about the chemistry of Mars and the mineralogy, we believe that most of the variations in the amount of equivalent water in those mid-latitude and low-latitude regions is tied up in minerals and is not so easy to access, although some would argue that if you can cook a hydrous mineral, you can release that water and then you can use that water. We have had a flotilla of spacecraft at Mars in orbit looking at the surface now for, going back to about the year 1997, I think, was when Mars Global Surveyor arrived. And we've been continuously watching the surface of Mars in that time. And one of the very interesting and exciting phenomena that we've been able to monitor is the creation of new impact craters. Obviously, impact craters are a major landform on Mars, but there's a whole category of impacts that seem to be revealing the presence of this shallow ground ice as a result of an impact of a fragment of a meteor or a chunk of a comet or something like that. And you see an example here. These are from the Mars Reconnaissance Orbiter high-rise camera, the high-resolution camera. You can see kind of a black splotch, which is an indication of a recent impact, and then the bright, icy-looking crater that shows up in the high-resolution images. Also, the series of frames that you see on the bottom there, those 6 frames, are two impact craters that apparently formed in single event of an object that's similar to a way split up into 2. And there was ice exposed in the bottom of these craters, but after about 100 days or so, that ice tended to fade into the background of the surrounding soils. And we believe that that's a combination of sublimation, again, because the atmosphere, the dry atmosphere of Mars likes to suck that exposed ice dry, and also the movement of perhaps dust to cover up that ice. But very clearly, this is an indication, and these are in areas where the neutrons were not able to see the ice in very shallow levels. So this is now maybe slightly deeper, maybe a meter or more depth. If you just dig a little bit, you're going to find that ice fairly close to the surface. A very recent result that I think maybe some of you heard about just a few months back was exposures of ice, again, away from the polar regions. This is, in this case, around 55 degrees south, so that's kind of in that boundary zone between the high and the mid-latitudes. But again, using Mars Reconnaissance Orbiter, combined image data with the spectral data that confirmed that this was indeed outcrops of water ice in these scarps. And the terrains here are, they have a lot of characteristics on their surface that remind us of what we call paraglacial or Arctic-type terrains, permafrost-type terrains on the Earth. And in many of these areas where we don't necessarily see this outcrop of ice, we see the morphology on the surface that's similar to these areas, which gives us a hint that maybe those areas also contain some of this ice-rich material in the shallow subsurface. Now we're going to talk a bit about radar. So there are currently 2 radar sounders that we sometimes call ground-penetrating radars at Mars. One is the MARSIS system on the European Space Agency's Mars Express spacecraft, and also the SHARAD shallow radar. which is on Mars Reconnaissance Orbiter. They're sort of complementary. One works in a low frequency range and is able to penetrate deeply. The other has a higher frequency, which gives it not so much penetration depth, but a higher vertical resolution. And we use these systems to basically take profiles that result in what looks like images that are sort of like a cross-section through the subsurface, and I'll show you some examples of that. But first of all, I want to show you a result that is from the just looking at the echoes of the that the radar obtains from the surface itself. I gotta look over here. Okay, so this is unfortunately the slide apparently got chopped up a little bit, but I think it still sends the message, which is that we're able to estimate the electrical properties of the upper now 10 meters or so. Remember, the neutrons are only looking at the first half meter. Here we're using this long wavelength radar, and we're looking at a few tens of meters, maybe 20, 25 meters, the average properties of that surface. And what our global survey using the MARSIS instrument told us is that in the northern hemisphere in particular, where you see those kind of bluish colors, we have a low value of this electrical property called the dielectric constant, the radar, basically the radar reflectivity. And this is consistent with ice. This is the same value that we see in the polar regions, but it gives us a hint that perhaps these, especially in the northern plains, that there may be a significant amount of ice in the upper 20 to 30 meters or so. Okay, so now I'm going to move on to some studies that we've done in this boundary region between the southern highlands and the northern plains, and you can see the latitude and longitude here, this area called Deuteronoilus mensae. What's been interesting about this region, going all the way back to the Viking days, is that there are features that remind people simply from imagery of glacial landforms. And so you can see the little box that points you to that area, and then you see this largish multi-ring crater there. I just want to emphasize the scale bar here by showing I think I have a Mac to PC problem here. Anyway, that area, this image, if you can see the scale bar, 400 kilometers, that black bar, from edge to edge here, this is about the entire western states of the U.S., from California to the state of Washington. So it is a very big place. Now, what's interesting is that these features that we call sometimes the Lobate debris aprons are these materials that seem to have been plastered on and then flowed away from high topography. And I'm going to zoom in on one of these here, and you can see this sort of high ridge and then this surrounding apron of material with what appear to be flow lines and crevasses and other kinds of features which are quite familiar to glaciologists studying glaciers on Earth. So going back again to the Viking days, it was suspected that maybe there was a role for ground ice in creating these things. So we went and we had a look with our radar system, and I'm going to have to move kind of fast here, so forgive me if not all of this is obvious or clear, but basically what you're looking at there in the top panel is this slice, this kind of two-dimensional vertical slice or cross-section through the terrain, and then in the lower panel you can see the ground track, which is an image in this case of where the radar was flying across. And so as the radar flies from left to right along that line, it's going over basically flat terrain. When it intercepts the boundary of this lobate apron, you can see that where those two arrows are, the signal splits into two, and you see one which follows the upper surface, but then you see also that lower one. That is the radar wave penetrating through the apron material and obtaining an echo from the lower boundary of it below. So typically, since it's a radar, we're looking at the time delay. We're measuring how much energy comes back at what time, and that doesn't automatically tell you how deep something is, But if you can estimate or have a guess at what the material is, you can say, okay, we know radar waves travel at a certain speed through ice. They travel at a different speed through solid rock. If we play around with that speed of the wave, then it tells us something about the material. So each of those arrows is pointing to a subsurface detection through these lobate aprons, these glacial-like features. When we take the value of the speed of the wave in ice, and we then convert this slice from time to depth, you notice all those arrows. All of those positions line up into a straight line. And really what's happening there is it tells us that we're probably on the right track, that in fact that using the speed of the wave in ice we're on the right track. We're probably looking at ice. Now, we have some other reasons that we might suspect that this is ice, and again, it goes back to the geomorphology that people have studied for decades. And also there are climate models that tell us in these boundary zones between the high topography and the lower northern plains, these are areas where weather systems